Okay, so last class we talked about Ising models and we saw several properties of Ising models. And the most important one was that for Ising models, the condition distribution has a very nice simple formula. Right? You have an unsupervised learning problem, you're getting samples. Each sample has D features, and we had to learn the underlying graph. And we said, okay, we're going to hold out one of those variables and try to predict that variable from the remainder. So we went from unsupervised to supervised. And that's a very important trick that gets used all over the place. But in our specific context, it simplified the problem for us to a regression style question. Okay. And today what we're going to do is solve that regression style problem while exploiting sparsity. If you don't want to exploit sparsity, then there's a different bound which is at GLM-tron, kind of where the dimension, the number of samples needed is linear in the dimension. Okay. But we want to exploit sparsity because we don't have that many. So that will lead us to Sparsitron, which is again kind of inspired by perceptron, but exploit sparsity. And then we'll talk about Gaussian gradient. Okay. And in terms of announcement, assignment 2 is graded on Gradescope. 3 should be up pretty soon too. And as I said last week, lecture 19 will only be on Zoom. So I won't be here in person, so just keep that in mind. Okay. All right, so where were we from last week? Okay, so let me just say again, write down what I said just now, which is, okay, we wanted, so input, our original problem was we given input x1 to xn from a sparse Boltzmann machine or Ising model. Right, and our output goal was learn the underlying graph. Okay, and there our hidden assumptions were, all of these assumptions are pretty well thought of. Right? We said we need to assume that the graph is simple in some way, otherwise the problem becomes ill-posed. So we said, okay, the graph G is sparse. Okay. In particular, sparse meant that each vertex has at most k other edges. Okay, so the max degree is bounded. And then we said every non-zero edge weight was between some numbers like half in absolute value. Right, if it's too small, once again, you will need a lot of samples just to notice even a small. Okay. And we went from here to solving a regression style question. Right, so what was that? So to a generalized linear model problem where we are given as input now points of the form x1, y1, x2, y2, all the way up to xn, yn, right? And the assumption is that the yi's are 1 minus 1 valued, and the probability that y equals 1 given a particular example x was a sigmoid function. Okay. And our goal was to find a u with small error. We're given samples like this, so it's kind of a regression problem, and our goal was to find a u with small error, and the error was measured in terms of squared loss. Okay. And if you know some statistics, this is called the conditional mean function. Like, usually don't talk about probability y equals 1, but you look at the expectation of the label given a particular example, you can assume the conditional expectation as some nice form, and then your goal is to kind of give a predictor for the conditional expectation. And this is useful in settings where even you expect the ground truth to not be deterministic. Even if I know the best predictor, the label still has some randomness involved. And that is actually possible in many cases. Right? So if I know the weather conditions today, maybe I can predict what's going to happen next minute, but not exact. I can say, okay, it's 90% chance that it's going to rain. The true predictor also gives out probability values for the day. Okay. So in such things, this is a very meaningful one. And there's a name for it in learning literature. These are called probabilistic concept model. So in learning theory parlance, when you say concept class, it's a class of prediction functions that you're trying to fit your function. Probabilistic concept just means that you expect your true predictor or best predictor to also be probabilistic. Like there's a distribution on the labels that you're trying to learn. Okay. Does it make sense? Any questions about that? All right. So we want to do this. And what are the assumptions that we have? The sparsity assumption on the graph means that W star is K sparse and non-zero entries are between 1, 2 in absolute value. Okay. And we said these two together imply that norm of W star, the L1 norm, is less than or equal to 2. In fact, this is with the constant. Let me say O of K. Yeah, this is fine. Okay. All right. So with all that, we ended up with the following question, which is what we're going to solve. Right. So the input for us is x1, y1 up to xn by n. And the assumption is that expectation of y probability okay, so let's assume the constant term is 0. As a vector, it's non-negative, and the L1 norm is 1. All of these, as I said, you can use standard tricks to reduce to this. Even in a regression problem, you can always assume these things without too much of philosophy about it. Especially if you're working with arbitrary distributions, this is never an issue. Okay. And our goal is to find a U such that the expected squared loss in the conditional mean function, that is in the probability value, is small. Okay, so this is what we want. So let me just any questions? All right, so let's see how we are going to do this. So what's the idea? The idea is to use multiplicative rate. Okay. And as I said, usually whenever you think of, you're optimizing over probability space, right? So since you suspect the truth to be a distribution on these things, you can interpret it as a distribution. Right? You have non-negative values which are adding up to 1. I can think of it as a distribution on the coordinates. Right? So you might shoot for finding a U, which is also a distribution. And I said at the beginning, whenever you're working in the space of distributions, like multiplicative weights update is kind of a nice method. It's kind of really an analog of gradient descent when you're working in the space of distributions. So the idea is use multiplicative weights method. And remember, when we try to think of multiplicative weights method, we can, try and use it from first principles, like, just define it and then analyze it from scratch. But we did some hard work before, right? We have this regret bound and so on. So we can try and exploit it. If you want to try and exploit it, we need to set up some kind of fictional experts game. And that's what we're going to do. So there is no experts game or anything like that, but we're going to set up some fictional experts. All right. And so let me talk about what that game is going to be. Right, so you have D features, right? And then you have the prediction label Y. Okay, so this is X1, X2, 3. Okay. So imagine we're not seeing the Y and we're trying to predict Y from these X. Right? And what we know is that let's first understand, what the qualitative direction should be. Like if W star is something and, if X1 is positive, what does it say about Y? Is it pushing it towards being 1 or is it pushing it towards being minus? Just some qualitative things to figure out. So what is sigmoid? Right, so sigmoid is basically, remember, you have 0 here, and then you have this beautiful shape. Okay. So as the inner product increases, Y is getting more and more towards being 1. Okay. And W star is all non-negative, right? You can even think of it as really just like averaging some K indices, but you don't know which K. Okay. So for, let's say if W star 1 is greater than 0, how would you expect Y to be correlated with X1? Like if X1 is positive, would you expect Y to be more likely to be 1 or less likely to be 1? More likely to be, right? So now you can say, somehow my prediction is wrong and Y is 1, but X1 is 1. What would you do? Increase the weight, right? Somehow it's kind of conforming, just kind of qualitatively, right? We'll decide the quantitative things later, but we have to first kind of understand why the qualitative. Then X1 plus 1 should increase the chance that Y is. Okay. So if you're trying to set up a learning with experts game, we need to set up the loss function. I'm trying to explain the reasoning behind how you could arrive at the loss function. At the end of the day, it's just a simple line. Right? Writing the line is easy, but I want to arrive at the equation in a kind of natural way, right? So we are going to use a fictional learning with experts game, where we'll think there are D experts corresponding to each feature. Okay. And so day one or example one. Right? Both are the same for us. When you see the example, we're thinking of that as the first round of the learning with experts game. Okay. So we get X1, maybe this is expert one, expert two, so on after expert D, and then we have Y, which is kind of like the truth. Okay. So this is X11, and then maybe the second coordinate was -1. Maybe the third coordinate was 1 again. Yes, I'm just writing down the vector in this row format. Okay. And we don't have any specific bias to begin with, right? Initially, we don't know about W star, so start with W0I all being 1/D. Right? All features get the same value. Essentially, you compute this inner product, and that will give you some guess on the distribution of Y. Okay. So predict say Y1 equals okay. So you try and compute the sigmoid, gives you some bias, and then that's your prediction. So this is your Y. You'll say 1 or -1, and it's not a fixed prediction you're making, right? There is some randomness here. Okay. Because you're expecting the truth to also be random, you're making like a random thing. All right. And then the truth comes out. Truth, the example comes out to be 1 or -1. I shouldn't say truth because there is randomness even there in the Y, right? The way the generation is going, there is some bias there. But whatever, we see the sample. Okay. And that's it. Now you have the first day gone. And the only thing that we have to do is decide what the loss functions. And then multiplicative weights will take care of everything, right? That's the oracle that we have to supply. And then the machinery of multiplicative weights will kick in and will be fine. Right? So we need to define loss of I, 1. For each expert, what is the loss that the ith expert will incur? Okay. So what do you think it should be? Any suggestions, guesses? Yeah.
So, observation. Or yeah, if the first weight for that feature is bigger, xi was 1, but y is 0, we should.
Right, but the issue with that is, I was saying there is a qualitative sense you want to go.
Right. Like what's the quantitative?
What's the quantitative one, right? And the thing that's important to keep in mind is that both of these have random. Right? somehow, even if you already had the exact W star, right? You don't want to be too aggressive with the updates, right? Because whenever if you have mismatch, if you update again, even with the true W star, you're not going to get the exact same label, right? Because just because the noise, you're trying, in some sense, there is a coin. You don't know its bias. That is what you're trying to guess. And you have the coin toss system. Okay. So what is the true thing that we expect the W0 to give us? We expect W0 to predict the somehow let's say W star tells us essentially what expectation of Y given X. It tells you what's the probability, and from that you can calculate the expectation. It tells us what is the chance of what is the chance that you see one compared to this. So if you think of extremes, it would be bad. It would be a bad mistake in this round if somehow W0, X1, the inner product is all the way here, right? And Y sample is 1. That would be bad. Because it's saying our prediction is that Y should be very unlikely to be 1, but the sample that we see is actually 1. So that would be a bad prediction. Okay, so that should be penalized more than saying we predict, we don't have much of a guess, we predict it should be half and half, and the truth is 1. Right? So it's not just 1 or -1 kind of penalty. We should compare the bias that you have. So if you play with this sort of logic that somehow you have to take into account how much odds are you giving to 1 or -1. Okay. So you end up with first let's think of this expression. What is this saying? It's saying if my sigmoid is in the middle and my true label is 1, that's less of a mistake than this is way out, in the negative direction. So the sigmoid is basically 0 and you see a 1. Right? So it's penalizing how far the prediction value is. Does it make sense? Qualitatively. And another way to think about it is now if I take expected loss, what is the expectation of Y1? It's essentially proportional to the sigmoid of W star, X. Okay, so something nice happens there. But you don't have to worry too much about it. You can just think of it this way. Okay. So qualitatively, you're trying to penalize where your sigmoid prediction is. If it's closer to the right side, then even if there's a mismatch in the label, you're fine. That's the net loss for the whole prediction. And now you have to allocate this to each of the experts. And here, what you said makes sense. If this is, somehow this is 1, but my XTI says -1, then it's bad. Right? The ith coordinate is saying -1, but the true value is 1. Somehow that should be like a loss. Okay. So if I remove the sigmoid, then it's basically the expression that you said. If y doesn't match the x coordinate, then you're giving it a loss. But I essentially want to center the y, so there's uncertainty.
Sorry, I'm confused by the indexing. One is referring to step one.
Yeah. So the superscript correspond to the example, and the subscript correspond to the feature coordinate.
Is the loss function not a function?
Oh, so this should be one.
I just thought it'd be like I in the general.
Exactly. Does it make sense? So without the centering, it's really the same update that you had in the homework. Saying if my ith coordinate is somehow mismatching the truth, then penalize that expression. But instead of just using that, I want to center it because even our truth has some randomness. Okay. So that's basically it. You assign these losses and I cover one. So loss of ith expert on day one is given by this. Update weights according to MWM. Repeat. Okay. So the final algorithm will be something simple. And for each example, you define the loss as okay, so you run multiplicative weights method to update the probability distribution on the expert. Multiplicatively increase based on this loss and keep repeating this. Alright. There's one small thing that you have to do, which is in the end, you don't just output the last set of weights that you have. And this is again because of something that happens in stochastic gradient descent too. You pick the best weight vector across the n routes. So this is something that we did even for stochastic gradient descent. If you remember, we didn't say, okay, output the last iterate. Then either you do the average of all the iterates or pick the best sort of iterate. And that's exactly what you have to do here. Pick the best iteration, best weight vector across the n rounds, meaning the one which has the least squared rows. And you can compute this by some holdout example. But it's not too important for us. We can not worry about it until we actually do. Okay. Yeah.
Chris, where do we use the weight vectors?
Right. So it will come in the analysis, but essentially, you'll see it like, if it's not negative, if the weights can be negative, the proof won't work. And it's also kind of intuitively makes sense, right? If the weight could be negative, then our intuition that whenever there's a mismatch, if this is 1 and this is -1, we're penalizing it, right? But if the weight is negative, it's actually doing the right thing. So it doesn't make qualitative sense, like intuitive sense, and the math also breaks. Okay. And as I said, you can always reduce to this case. So we're starting with these. And in the end, I'll tell you the full algorithm too, because it's so easy to, it's just like 10 lines. So even without this negativity assumption, it's pretty easy to do. Okay. Any questions about it? So that's the full algorithm for Sparsitron. And if you want to learn Ising models, of course, you do it for every vertex. So you do it for like these types. Okay. So what are some nice aspects of this algorithm? The first thing is, what is the runtime? What is the runtime of the algorithm? Yeah, exactly. It's right. So its runtime is O of n times t. Right. In each iteration, you have n rounds. In each iteration, you have to basically go through every feature and update its weights. Okay, so it's n times t. And remember, we said, like, we're thinking of this scenario where n, the number of rounds or the number of samples, is way, way smaller than the total dimension. T is like 1 billion, and the number of samples is maybe like 1,000. Okay. All right. And what can we say about what this algorithm does? So the simple algorithm actually does remarkably well. And the theorem that we're going to show is so in the analysis, you don't actually need anything beyond, but if sigma is sigmoid, but let's work with the sigmoid, then for n greater than or equal to O of, for some c times log d by epsilon squared iterations, we have, so let's call this best loss vector W. The loss is going to be pretty small. Okay. So if you want to get epsilon error, I just need to run like log d over epsilon squared. For any questions about the statements, you're getting this amazing savings in terms of the number of samples. It's only d as a log d as opposed to d which you need for, like, let's say least squares regression. Why are we able to do this? Because of sparsity. We have this assumption that W star has L1 norm at most 1, or really that is D sparse. Okay, so let me put that condition explicitly again here, just so that. Okay. All right. So let's prove this. The proof, as I said, we already did the hardest part, which is in the analysis of multiplicative weight method. We just have to kind of suitably apply. Okay. So the idea is to use the regret bound for MW. And what is the regret bound? Remember, the regret bound said, no matter what your loss functions are, the expected loss of a multiplicative weights method over any number of iterations, any number of days, is close to the loss of the best expert. So you have D experts, look at the total min loss that any expert has. The gap should be at most square root n times. Right, so this is the regret bound that we had for MW. And this has nothing to do with Sparsitron. This is just anything, as long as you have loss functions, this bound will. And now we have to connect, what this is doing to our specific setup. Okay. Somewhere this squared loss should also show. Right. So we have two terms. One is this expected loss. We need to kind of somehow connect that to that expression. And then we have this guy here. We have to somehow understand what this means. Okay. All right. So let's first look at the part one. So what is the expected loss of multiplicative weight method on day T? Right. So what is the expected loss? Well, we have a formula for it. So the expected loss is probability that a particular expert is picked times the loss that expert incurs on that day. Okay, so we said L of I comma 1 was the loss incurred on day 1. L of I comma T would be the loss of the ith expert on day T. And just formulaically, the expected loss is probability that a particular expert is picked times whatever loss I think. Okay. And we know what this is. What is the probability that an expert I is picked? Is actually the weight vector, after normalization, but we're already normalizing things. So this is just going to be WT minus 1 times. Right? So here, we are normalizing things just so that I don't have to carry around the denominator. Okay? Times L of I. Okay. And what is this L of I comma T? We defined it in some nice way. When we defined it, it was kind of intuitively done, but you'll see it fits like a glove with the math. All right. So you have YT times was minus YT sigmoid of whatever prediction that we made times okay. So that was the definition of our loss. All right, whatever, this looks somewhat tedious, but I can simplify it a little and write it as and the sum is again just the inner product. So the expected loss on day T is whatever the centered thing is times the inner product itself. Okay. So this is an exact equality. So as a result, we get total loss of MW after n rounds is okay. All right, so that kind of gives us some control on the left hand side. And now we have to connect what the summation thing is. And so what is the best expert loss? Right, so we are looking at min over all coordinates of the sum over all the days of the individual losses. Okay. Right, so if you think of this as a vector, then what do we have? So we have like, so you're looking at the min coordinate among what is they do p comma I or I? Right, so this is total loss of expert 1, total loss of expert 2, so on. And we have to take the least coordinate among all of these things. All right. But somewhere we had to bring in W star into the picture. Right. So the only thing that we know about the underlying data model is that the conditional distribution satisfies some formula which is given by this W. Okay. So how can I bring that into the picture here? I mean, in the homework solutions also you had to do something similar, right? Where when you're comparing the loss of the best expert, you had to take the minimum over all of the coordinates. Right? Taking the minimum is only going to be less than or equal to doing any weighted average. Right? So if I say, okay, what is the minimum score among all of you? It's always going to be less than or equal to picking a random person and asking that person. No matter what distribution I have. Pick a random person and ask your score, it's at least as big as the minimum, just by definition. Right? So in particular, this is less than or equal to W star 1 times the loss of the best expert. So loss of the first expert plus W star 2 times okay. So why is this? If I have a vector like this, and P is a probability distribution on D, then for any probability distribution on the coordinates, this inner product is always at least the minimum. Okay, so we're just using that as applied to W. Okay. Any questions about this? Yeah.
Like, I understood the example of you saying like the score of like all of our test scores, but something's just not making sense.
So what is this saying, right? So P is a probability distribution, meaning the summation of the PIs is 1 and is non-negative. So I can think of this inner product here as I'm picking a random index I according to the distribution P and checking what is Li.
He's like, instead of randomly choosing if he's like a weighted.
Yeah, exactly.
Choosing.
Exactly, right? And if you want to do it formally, I can say, what is summation P come L? This is summation I equals 1 to D, Pi times Li. Okay. And each Pi is non-negative, right? So I can say this is at least Pi times the min Lj. And by definition, each Li is at least as big as a min.
Like a weighted average.
Exactly.
Say that.
And now the min comes out because it doesn't depend on the summation. And what is summation Pi? 1. Okay. So we are using the same thing with W star instead of P. It's true for any distribution. So in particular, it is also true for W star. All right. So loss of best expert is less than or equal to we have this somewhat messy looking thing, but let me try to, it's a double summation, but as you'll see, it kind of becomes nice in a second. Right, so you're looking at the total loss of each expert and then putting the weight. Right, I just wrote down that. The loss of the best expert is at most this much. And to simplify it now, I'm going to just change the summation order. Okay. And what is this L of I comma T? Once again, we had the closed form formula for it. I'm just substituting it. All right. So this is summation K equals 1 to N of YT. If there's a minus. So you're adding up over all N base of this difference again times the inner product between W. Okay, so if you compare it with what we had, it's a very similar looking expression, but instead of having WT minus 1 here, you have W. That's the only, right? Okay, so let me call it equation 2. We call this equation 1, and then we have the regret bound, which is let's say equation. So combining 1, 0, 1, and 2, what do you get? So we get the expected loss of our algorithm, which was this formula is at most the loss of the best expert plus some constant times. Okay, this is thing that we, right? We just, this is the total expected loss. This was an equality, and the loss of the best expert was upper bounded by this, and this is the regret. Okay. We can now kind of simplify the calculation a bit and say, well, this is true. I mean, basically, this implies I'm going to bring that right hand side term on the other side so that I have nice, and I get okay. After all the calculations, the expression looks kind of neat. You're looking at what's the true, what's the y that you observe minus the centering, your predicted centering, times the true mean minus the predicted. And the true inner product minus the predicted. Okay. So far, all of our calculations hold for any given data set. Now, fix x1, y1, x2, y2, and so on, then this calculation holds. Right? But what do we know about yt? What is its expectation over the data set? If you do some calculations, you will basically get it's essentially like right? It's just the probability that it is 1 minus the probability that it is minus 1. Okay. And what do you know about this? This is sigmoid of W star times XT. Okay. And what is this guy? Minus 1 minus sigmoid of W star. Okay. So what you end up with is 2 times sigmoid of W star comma XT minus. Okay. So the expected value of yt is this 2 times sigmoid of W star comma XT minus. So far, everything seemed to work well, except now if you look at this minus, there is a mismatch in terms of this constant, right? So, as I said, the intuition and the math fit almost like a glove, except for this constant shift, right? But I didn't want to give you the formula upfront and see the correction that you need from the analysis. So if I plug this in, then there is a slight mismatch, right? There's a sigma here, and there's a 2 times sigma W star here, and then this constant. Okay. So the way to fix that is you just need to change what your shift is going. Okay. So let me say I'm going to define my loss as some sigma prime, maybe I'll put a bar here so that you don't have to prime with else. Where sigma prime of A is 2 times sigma of A. Okay. So I'm defining a new function which is just 2 times sigma of A minus. Okay, so the same reasoning, everything, but I want the math to kind of follow properly. So based on the analysis, I'm going back and just kind of changing this constant. Okay. Everything is just the same again. I'm going to put sigma prime here and prime here, prime here. Okay. So this is sigma prime. Right? Okay. So now what does this equation imply? So the bound that we have is, if I take the expectation over the data set, then over n days, so the expectation of y d is given by this formula. I'm just going to plug it in. I get w star comma xt minus, we have wt minus 1. So we have wt minus 1. Okay. So this is with the sigmoids times the difference between the inner products without the sigma. Right. So because y itself is a random variable, its expectation was the sigma bar, which is like 2 times sigma minus 1. And what we're getting is the difference in the inner product with sigma applied times the difference in the outer. Okay. This still seems a little messy, far from what we want, which was just a square distance between the sigmoid. So what can we do sort of fix that? Well, here's where first let me state it for a sigmoid and and this is the sigmoid function. Okay. So what would the scaled or shifted version sigma bar look like? Yeah.
Be between.
Exactly. It would be between, it would go to 0, right? And then it would be -1 and 1. You're just multiplying it by 2 and then kind of shifting it down by 1, right? So this is what a barrier. Okay, so the curve looks like this. Okay. And now, what can you tell me about so the expression that we have is still kind of cumbersome, right? And there's a difference between things which have sigmoid applied to them and without the sigmoid applied. Seems messy. But let me ask you a question. We want to simplify it somehow, but before simplifying, can you at least tell me something about the sign of this? Is it positive, negative? What can you say about it? So, like, let's say I pick 2 points. Maybe this is A, this is B. Sigma of A minus sigma of B, or sigma bar even. This is going to be negative here. Right? You know, sigma bar is on the left-hand side, sigma bar B is on the right-hand side. Right? But what happens when I multiply with A minus B? Positive, right? So in fact, this is always positive. Why? Because it's a monotonically increasing function. A is more than B, then both of them will be positive. A is less than B, then both of them will be negative. Okay. Right? And in fact, it's not hard to show that this so let me state it as a claim. So the function, kind of a smooth function, its derivatives are always bounded by 1. Okay, so it's 1 Lipschitz, which implies essentially what this is saying is your function is such that maybe because you multiplied by 2, this should be saying the change between the function values is always at most 2 times the change in the argument. It's not like a crazy function which is jumping up suddenly, right? It's a reasonably smooth function. In fact, the max change you will observe is near the origin, right? Like the slope is highest at the origin, and even there it's not that. Okay. And it's only, I mean, there's 2 just because it's 2 times the same. So what does this mean? This implies that the product of these 2 is at least half of the squared distance between the. Because the distance between the actual absolute values is actually larger than half of the sigma. Okay. So let me call this equation 3, and this is equation 4. So from 3, 4, what do we get? We get the expectation over the data set of the sum of the losses, sigma bar, okay. So I'm using it with this being A and this being, right? It's really the same form, sigma bar of A minus sigma bar of B times A minus B. Okay. So now we are really, we now have a form which is pretty much like what we wanted. The squared distance between our prediction minus the truth is kind of bounded in some sense. the sum of the square distance is bounded by square root of n times. Okay. So far so good, but now how can I finish the suggestions? We have a bound on this sum, but what did our algorithm do? It picked the best predictor. Right? It didn't output like Wn. It said among all of these individual iterations, pick the one which has the smallest loss. Right? So that implies that the loss of the best predictor. Right. Okay, so first, just interpret it. This is really saying but it's saying if I add up all of the losses, then that is bounded by square root n times 1. Right. So the mean loss is less than or equal to the sum is at least n times the min. So which is some constant divided times square root ln d by n. Right. So if n is much bigger than ln d by epsilon squared, then this is. Any questions about this? So I'd say the magic is that you use the regret bound with some intuition. You had some intuition for okay, the y should shift this way based on what xt is saying. We don't want to use the exact value. We want to center it based on the prediction. And then we looked at the math, and somehow there was a missing factor too. So we went back and corrected it, and everything just followed without any change up. And there's this somewhat hacky thing where we kind of pulled out this inequality and then simplified it to give the form that we want. There's also a more principled way to come at this, but I think it's a more long-winded story than just using this as. At the end of the day, we're getting errative at most epsilon as long as n is something like ln d or n, which is what we wanted to show. We said the Sparsitron gets this guarantee that the total error is at most epsilon when n is sufficient. Okay. Any questions about this? Right. Okay, so let me say a couple of words about the algorithm. Right, so in summary, maybe let me copy that here. Okay, so this is what we showed. Then okay, sigma is sigmoid, and then something like this happens, then Sparsitron satisfies this. Now, can you tell me where we used? Did we use any special properties of sigmoid in this scenario? Was sigmoid somehow special throughout this proof, this analysis, where did sigmoid being sigmoid, the exact formula, did it play a role in the analysis? What do you think?
One bound.
Right, so pretty much the only two things that we use were, first, it is monotonically increasing, right? Because we wanted this to be monotonic. Okay. And then we just use the fact that it's linear. Okay. So, we're not going to do it, but same works for any sigma which is bounded between -1, 1 is non-decreasing and essentially if it's L Lipschitz, your sample complexity becomes like C times L squared times log. So nothing else really changes. Okay. There's nothing, at least this part is not specific to sigmoid, but you can do the generalized linear regression fitting for any sparse function as long as the activation function satisfies these three problems. So you can have things like tanh activation, ReLU activation, cutoff, ReLU activation, which is clipped off. All of those things will still have. Okay. Any questions? Basically, I'm saying you don't have to have like this shape. I could have something like maybe this. That's also fine. I could have this. That's also fine. As long as I don't have like a steep jump, which destroys the Lipschitz. Okay. All right. So let me summarize what we did, and then I'll tell you one other thing. Okay, so what did we just saw? We saw how to solve sparse generalized linear models with logarithmic. Right, as far as linear regression goes, it's a very fundamental model, and putting an activation function after the linear sort of concept, that seems like a very natural next step. And what we just saw is how to solve sparse versions of it with only logarithmic sampling. And then once we have this, we know how to use this to learn Ising models and or Boltzmann machines. Okay. And something we did not discuss, but you can also apply Sparsitron to learn Markov random. P-wise. Okay, so for higher T, you have to do something slightly different, like you don't get a simple GLM. You get a GLM kind of thing, but with polynomial kernel, and if you know what that is, then you can use that. Okay. And both of these you can do with nearly optimal sample complex. All right. And runtime is quadratic. We don't know if that's the best possible. As I said, even when there's a single edge present, the best is like b to the 1.72. And if you have multiple edges, let's say even if you have, let's say, 3 edges, it's not clear how to beat the quadratic thing. I think beating quadratic for some simple structures like trees, etc., would be very interesting.
Or like to use this in the Ising model, like would you just clip all the bits that have like some bit less than them?
Yeah, so essentially you can clip them because things which are less than that. I mean, there's a statistical reason too. But to simplify things, we started with the assumption that you have this lower bound on the weights. And the reason, part of the reason is that if it's much smaller, then it's not going to affect your error anyway. So that's something that we are not doing, but you can reason along those lines. And you should be using this model only when the non-zero weights have some non-trivial value. If the non-zero weights are like 1/d and you want to recover the graph, you will need D sample. There's no way around that. In fact, you can state the bound so that it depends on the least value. So in some sense, if you actually look at our paper, what you get is given n samples where n is greater than this, you find new approximate weights a hat ij. There was an underlying graph weights that you're trying to learn, but you find some new weights such that the difference is. Okay, so now, if the true weight is big enough, then you'll notice whether it is 0 or not. But if the true weight is also very small, your weight will also be small. Okay. So it's just that it's less than or equal to, you're kind of getting a pointwise approximation. Any other questions? No? Okay. So if there are no other questions, this is what I wanted to say about discrete undirected graphical models. Remember, we started out with this assumption that you have this underlying dependency graph, and then you have these features, they satisfy this conditional dependency and independence, right? And so what we did so far, you can extend it to, like we stuck to 1 - 1 valued coordinates, right? But you can extend it to multiple coordinates too. Like it need not be 1 - 1, it could be AC, GT, and so on. But that does not extend to real valued things. Okay. When the things are real valued, the integration becomes a lot more cumbersome, and sometimes it is not even well defined. You have to be a bit more careful. But fortunately, there's one really beautiful special case, which is the setting of Gaussian graphical model. Okay, so which is just saying that I have a graphical model, I have a distribution, which once again satisfies some dependency relations. But each individual coordinate has the standard Gaussian distribution or some Gaussian distribution with some variance. So the overall distribution has some Gaussian distribution, but there's some dependency graphs. Okay. So we're going to now talk about learning and given samples from this, can you learn that? Right? Okay. But first, some basics about Gaussian or the normal distribution. It's no exaggeration to say this is probably the most important distribution probability in machine learning everywhere else. So what is it? So in the univariate case, it's usually written N0 sigma, right? And okay, let me first state it for 1 is just given by the PDF is Okay, so this is the formula for the PDF. Okay. If you ever wonder why the square root of pi is coming up, it's a beautiful problem to figure out. If I tell you that the density is proportional to this, what is the normalization constant? You can do some calculus to figure it out. There is a very nice video on YouTube, like giving a geometric derivation of this integral, but let's not go into that. And if you have something like sigma squared, you get. If you want to draw it, the PDF looks like you have 0 here and the famous bell curve. Okay. This is the univariate case. In the multivariate case, so what if I want real value, like multiple coordinates? And even in multiple coordinates, fitting a Gaussian distribution is the most sort of used method. Like if I don't know anything about the underlying distribution, I want to make some assumptions, just try and fit a Gaussian makes most with minimal information. So here, what does it mean? Like, I have a random variable x over Rd with the d coordinates. And if it's IID Gaussian, what would it mean? It would mean that each coordinate is independent and has a normal distribution. So that is denoted N0, identity. Identity just means that the sides are independent and distributed as N0. Okay, so each coordinate has a distribution. So in particular, the PDF in vector form becomes okay, because it's independent, you would multiply all of these individual things to end up with this form. The multidimensional Gaussian distribution has this PDF. So the value of x, the probability of seeing a particular x, only depends on the length of the vector x and has some scaling. Yeah.
So in the d-dimensional case with the second R.
Yes, exactly. Right. So this, in the case of identity, these are independent. Right. But in many multivariate cases, you don't have independence. But there is correlation between. Okay. So here, the covariance xi and xj are all 0 if I is not equal to j. And of course, expectation of xi squared is 1. Okay, so that's a thing. If I use this particular formula, then the expectation of x squared turns out to exactly be. That's a complicated integration you have to figure out, but it turns out. And it's always symmetric. The probability of seeing x is the same as seeing minus x. Right? Because there's a square here, probability of seeing x is the same as minus x, so the mean is always 0. So the positive and the negative things will cancel out. Okay. And the same is true even in the multidimensional case. So you have these things, and then you also have the expectation is. Okay. But what if I want to have a multivariate Gaussian distribution where things are correlated? So that is denoted as the most general form of the Gaussian distribution is the multivariate Gaussian distribution. And these are parametrized by the covariance method. a D by D matrix. It's called the covariance matrix and denoted N0 sigma. Okay, the mean is still going to be 0. And the covariance matrix is whatever the sigma matrix. Okay. And the PDF is now I don't want to, I'll just say what's the most important thing, which is that it's proportional to X transpose and sigma inverse. So sigma is a matrix, sigma inverse is a D by D matrix, X is a vector. Right? I'm looking at X transpose times a matrix times X. So this is a scalar now. Right? So you have X transpose is a vector like this, right? And then sigma inverse is a matrix, and then you multiply all of these things, you get a scalar which is going in. Okay. And once again, this is symmetric in the sense that the probability of X and minus X is the same, so the mean is 0, so they will cancel out. The expectation of X is actually 0. And the expectation of any two coordinates is actually just sigma. So that's why sigma is called the covariance matrix. Because it tells you exactly how correlated are Xi, Xj directly. Okay. Any questions about this? You probably have seen Gaussian distribution before, but I just want to set up the notation right. Now, this should ring a bell. This expression should ring a bell with something that we saw earlier. Okay, so why is that? I want to say we can think of P of X. It's saying it's proportional to. We want to write it as a summation. Let me call sigma inverse as theta. Okay, just for actually, let me not do that yet. I mean, this is a compact notation in terms of vector, matrix, vector product. But if I expand it out, what does this whole thing become? It's minus summation I comma j of xi times xj times sigma inverse x. This, you can check it, you're multiplying each row with, x1, the first row with x1, second row with x2, third row with x3, and so on. And then you're multiplying all of the columns and then adding up everything. Right? So the sum is actually equal to this. Right? This is equal to X transpose sigma inverse. Right? So this is like a quadratic form that you have in the expression. Did we see something like this before? Yes, no? How did we define Ising model? Well, Ising model, if you go back, let's see, where was it? Right, you have a summation over Aij times Xi times X. Right? So we have something similar in the multivariate Gaussian distribution, but you have the sigma inverse there first of all. But you still have the summation Ij sigma inverse Ij times Xi Xj. In the exponent, you have this quadratic function. Right? So just keep that in mind, like, there is some sort of similarity between this and what we saw. And one other thing to keep in mind is not all matrices sigma are allowed in the definition of multivariate Gaussian. Okay, the covariance matrices are special. Yes, sigma is a covariance matrix if and only if, right? Two things hold. One, what's the simplest property of the covariance matrix? Yeah, symmetric, right? Because the way xi times the expectation of xi times xj is the same as expectation of xj times xi. Okay? Sigma is symmetric. Okay. What else? Yeah. All the values should be between. Only the diagonals, right? The off diagonals can be negative, right? So, like, imagine I have, like a distribution which is x1 and minus x1, and this is n01. Okay. So let's say this is my random variable. And why don't we just do this calculation? Right? So this is x defined as x1 and minus x1, where x1 is n01. Now, what is the covariance matrix of this? Yeah. On the diagonal, but on the off diagonals, you get minus, right? Because what is expectation of x1 times x1? 1. That's just the variance of x1. The same here, but what's the covariance of these two? It's minus x1 squared, which the expectation is minus 1, right? So it's not necessary that all of the entries are non-negative. The diagonals are definitely non-negative, because if I put I equals j, I'm getting expectation of xi squared. The expectation of any positive value quantity is going to be positive. Okay. So, at least that is true. So let's say the diagonal entries are greater than. What else? Yeah.
It has to be positive, semi-definite.
Right. So basically, if you the most non-trivial property that sigma satisfies, in fact, this is true not just for multivariate Gaussian distribution, but you can take any vector value random variable, you can define a corresponding covariance matrix. Okay. For that, you satisfy the following thing, which is because sigma is symmetric, then all eigenvalues of sigma are, okay, let me state it this way. Sigma is quote unquote positive semi-definite, or PSD. As far as matrices go, this is perhaps the most important class of matrices after symmetric matrices. In case you haven't heard about it, I highly recommend kind of looking at some of those properties. Okay. So let me, we don't need many of these things for what we're going to do later on. But I just want to get you, like, we're going to show some very strong results for learning Gaussian graphical model as opposed to learning Ising. And at some point, I want you to go back and think, okay, well, where did the magic happen? Somehow you have this much stronger results here versus what you had for discrete. The change is because of this PSD. Okay. Yeah. Exactly, it does, right? So let's, it's not trivial though, to show it. Okay, so let me state it. So there are various definitions of being PSD, or positive semi-definite. So sigma is PSD. It's actually only defined for symmetric matrices. So a symmetric matrix A is PSD if and only if one of the following holds. I mean, they are equivalent really. The first thing is all eigenvalues are non-negative. Okay. So when all if I just tell you that all eigenvalues are non-negative, going from there to saying that all diagonal entries are, that is not true.
It's the definition I was most familiar with. I transpose A by.
Exactly, right? So there's this, there are two definitions. I think to do the thing to show that they're equivalent, we need to use eigenvalue decomposition.
The other definition.
That one follows here. Okay. So what's the other definition? So the other definition is that positive semi-definite matrices actually define distance metric. You can use them to measure distances between points, and which are not like just standard Euclidean distances. What if my space is somewhat distorted? You can quantify that in some way. In fact, this is actually done. This is called Mahal and Opis distance based on covariance matrices, especially. Okay. So the other property, which is equivalent to all eigenvalues being non-negative and being symmetric, is that for all vectors, this is an infinite set of inequalities. For all vectors V transpose AV is non-negative. If I tell you that all eigenvalues are non-negative, this is like almost somehow like n, if it's let's say it's a d by d matrix. Saying all eigenvalues are non-negative seems like, okay, it's D conditions. Compute eigenvalues, they are non-negative, but this implies a bunch of inequalities, like an infinite number of inequalities. Saying for any vector V, no matter what it is, it could have negative entries, it could have positive entries. But if I compute this inner product, I always get something. Okay. So this is V transpose AV is summation I comma j VI times Vj times AI. If I compute this quadratic form, you always get something. Any questions about the definition? Okay, so let's play around with this definition a little bit, and next week we'll dig into, next class we'll see how to use it or something. So plane A is PSD implies all diagonal entries are non-negative. Why? How can you prove this from PSD-ness? Yeah. Exactly, right? So it's this inequality holds for every V. I can put in any vector V here, right? So apply it with V equals the vector which has zeros everywhere except in the ith coordinate, where it is 1. Right, this is the standard basis vector EI. Then we have EI transpose A times EI is AI, which we know is non-negative. So all of the diagonal entries. Okay. And we just saw that we take the matrix 1, 1, minus 1, minus 1. Right? So this had this was a covariance matrix of a Gaussian distribution at x1 and minus x2. Let's check if it is PSD. So another example, let's say A equals this, mu sigma. What is V transpose sigma V? So let's say I have V1 times V2, and then I have 1 minus 1 minus 1 times V1 times V2. What do I get? I get summation I comma j equals 1 to 2 vi vj times sigma ij, which is I get v1 squared plus v2 squared, when I equals j equals 1, and then the cross terms are minus v1 v2 minus v2 v1, which is okay. Just as a sanity check, this matrix is PSD because V transpose sigma V is actually equal to V1 minus V2 whole square, which we know is always not. Right, this is clear as a quantity. So this implies sigma is PSD. And for any Gaussian distribution, the covariance matrix is PSD. And given any PSD matrix, this formula defines a valid distribution, which is the Gaussian distribution.
Is it possible to have non-invariant?
Yes, for sure. Yeah, so there you're right, absolutely right that this is not exactly technical. So you just have to project out the kernel. You'll end up with a Gaussian distribution where in the coordinates where you have 0 things, the kernels will be exactly. Yeah. Okay. All right. So this is some basic facts about multivariate Gaussian distribution. And the next class, what we're going to talk about, or let me say one last. Now, so stat 101 problem. I think the most basic side, it's even more basic than linear regression, is given samples, let's say, x1 through xn from some multivariate normal distribution or Gaussian distribution. I want to estimate sigma. Give me some parametric estimate of what the covariance matrix is just from this sample. If I tell you this, what would you do? We don't know what sigma is. We're just given samples from this multivariate Gaussian distribution, and I'm asking you to estimate what sigma is. What would think about what you want, right? We have a formula for what sigma ij is. We know sigma ij in expectation is expectation of xi times x. But if you want to estimate it, what can I do?
You just take like calculator for each point.
Exactly. You're getting samples from something and you want to estimate some average. So let's try a sample average, right? And that's called the sample covariance matrix. So idea is estimate sigma ij as the average over the n samples of this guy. And just use my samples to estimate this. And there's a compact way to write this. So the formula is you estimate it as if I take the vector and multiply it with transpose, each time I get a matrix and you just average increase. Okay. So this is the most basic estimate for the covariance matrix. Right. This is called the sample covariance matrix. Kind of a standard thing that you do in any sort of centering stuff and so on. You complete the sample covariance matrix, maybe you do something. And there is a theorem which says that if n is much more than or b, then sigma hat is closed. if I have a linear number of samples, I can estimate Gaussian distributions extremely well. Right? So at the very least, like just a question of learning multivariate Gaussian distributions is very easy. Just come to the sample thing, I get the parametric estimate of the covariance matrix that is close to the true thing. The only catch is that you need linear numbers. But remember, our whole thing is many cases we don't have a linear number of samples. The dimension is 1 billion, but you have only 1,000 or 10,000. What are you doing? Okay. So what we're going to do next case is find some assumptions on sigma under which you can get similar guarantees on estimating Gaussian distribution, the parameters of the Gaussian distribution, but with almost logarithmic numbers, just as we were doing. We can motivate it from the angle of learning graphical models or just straight up from the question of learning Gaussian distribution. In fact, people have approached it from completely different fields for this. Okay. So that's what we're going to talk about Monday, on Wednesday. Okay. And remember, Wednesday, the class is on. All right. So yes, I'll see you all for the exam, but until then, on Wednesday, we are